Hello, let's continue with section 7.4, the binomial theorem. So objectives are explaining the powers of binomials using Pascal's triangle and the binomial theorem. So before we start, I just want to warn you that the notation looks pretty ugly, but don't let that throw you off. Um, it's if you take it step by step, it's not so bad. Also, have your calculator handy because you will have to use it or learn how to use it. Powers of binomials. A binomial is an algebraic expression with two terms. In this section, we will determine patterns that exist in the whole number powers of binomial expressions that will allow us to find relatively high powers of a binomial without multiplying the binomial by itself numerous times. So it saves the trouble of FOILing. So no FOILing process. To begin, let's consider the following list of powers of the binomial. So a binomial is just two terms. They can be added or subtracted. But if we raise them to a power, well, anything to a zero power is 1, with the exception of 0. If it's raised to the first power, it's itself. If it's squared, we've seen that a lot when we FOIL. But third power and fourth power, there are patterns we see. However, we don't see those problems as often. Yet, at least yet. Alright, so let's notice some patterns. We see that every number or every term has been raised to the highest power, the beginning and the end. But let's take a look at our x. It starts with a 4, goes to a 3, 2, and then first power, and then it's gone. And it seems to go in reverse order for the y's. There's no y, so think of it as a 0 power, and a y to the first power, 2, 3, and 4. So it seems like as one power decreases, the other power of the second term increases. And we'll see that happen with binomial expansion. Having some background in algebra, we should be able to recognize the first few powers of a binomial from previous studies. However, we will use the patterns displayed above to continue the list to higher powers. First, starting with the binomial x plus y squared, let's consider the pattern of the variables of the right side of each equality. So here we have our x's are written first, and then our y's second. We see that our x's, well, if it's squared, it starts squared, and then it slowly goes down by 1. And my y's, it goes up by 1 each time until it reaches its power. We notice the same thing for 3. It starts with a 3 and goes down 1 each time. Similarly for the y's. The y's work in backwards order, meaning they go up until you reach your exponent. In each expression on the right, the first term x with the same power as the power of the binomial, decreasing by 1 for each term moving to the right. The variable y, the first term has no y term, but the power y increases by 1 for each term moving to the right until reaching the same power as the binomial. In general, for each of the following x plus y, the variables will have the following patterns ending when the power of y reaches n, meaning whatever exponent you have. So that's our exponent. We'll know when that second number, if it's going up by 1, reaches its ending, or the value of the exponent. Secondly, we need to find the coefficients of each term. For relatively low power of the binomial, we can use Pascal's triangle to determine the coefficients. The following first row of Pascal's triangle, where each row starts and ends with 1, and each other number is found by adding the two numbers directly above it. So let's take a look at Pascal's triangle. You build it by writing a 1, and then you're going to enclose it with 1s. So starting with the 1, now I want to look at the numbers directly above it. 1 plus 1 gives me 2. and we end with the 1. All right, we start with the 1. 1 plus 2 gives me 3. 2 plus 1 gives me 3. And we're done, so then we end with the 1. Again, we start with the 1. 1 plus 3 gives me 4. 3 plus 3 gives me 6. And 3 plus 1 gives me 4. We reached our 1, so we close it with the 1. And we keep doing this as many times as we want. This is called Pascal's triangle. Using the variable pattern along with the coefficients from the proper row of Pascal's triangle, we can expand the powers of binomials. Example 1. Write out the expanded expression of each binomial using the power of each binomial power using Pascal's triangle. Okay, so let's do things separately. Let's determine our x's and our y's, our first term, and then we'll worry about our coefficients. So our variables will follow this pattern. If it's helpful, I like to write it vertically. For some reason, that helps me more. So I'll start with x. Your first one is to the power you have, so 7. That's going to be raised to the 6, 5, 4, 3, 2, 1, 0. Then for my second term, I work backwards. So for the y, I start with 0, 1, 2, 3, 4, 5, 6, 7. And if we clean it up, well, we see that x to the 7th power, that's just x to the 7th, and y to the 0 power is 1, so that's gone. We get x to the 6th power, and then just y to the 1st power, x to the 5th power, and y squared, x to the 4th power, and y cubed, and so on. And we have all of them written here. All right, so that's our variables. Now, to determine which row of Pascal's triangle we will give the coefficients, we must recognize that the coefficients of the second term of each expanded expression matches the power of the binomial. So we see a 7. We look at our Pascal's triangle. Since we're raising it to the 7th power, we want to choose the row that starts with a 7. That's a good way of thinking about it. But really, this lines up with the exponents. So 0 power, 1st power, 2nd power, 3rd power, 4th power, 5th power, 6th power, 7th power. So that's another way of recognizing it. All right, so that's the row from Pascal's triangle that will line up with our binomial expansion. So let's go ahead and put them together. Let's just go ahead and match them up. So my first term, second term, third term, fourth term, fifth, sixth, seventh, and eighth. You know you're on the right track when the number of terms equals whatever your exponent is plus 1. All right, so putting all this together, we have 1 times 7 plus 7 times x to the 6th power times y, all the way to our last term. So this is one way using Pascal's triangle. All right, so far examples have been really pretty because notice that there's no number in front of our variables. Let's go ahead and take a look at example B. 2x minus 3y raised to the 5th power. In order to use the same pattern we have so far discussed in this section, we must consider the expression 2x, so our first term only, plus negative 3y raised to the 5th power, where 2x is the first term and negative 3y is the second term. So just like before, let's go ahead and set up our variables, our term from our binomial. And again, I don't know why, but writing it vertically makes a lot more sense to me. So let's take my first term, that 2x. So I have 2x. We start with whatever exponent you have. We have the 5th power, so we'll start with a 5. Then I have 2x to the 4th, 2x to the 3rd, 2x squared, 2x to the 1st power, and 2x raised to the 0 power. Notice I write it in parentheses, and that's really important, especially for this type of problem. And then we have our negative 3y. Negative 3y raised to the 0 power, negative 3y raised to the first power, negative 3y raised to the second power, negative 3y raised to the third power, negative 3y raised to the fourth power, and negative 3y raised to the fifth power. Good, we ended with the number we're supposed to end. All right, something to keep in mind as we work with these exponents, remember that the 5 applies to the 2 and to the x. So that's 2 to the fifth power and x to the fifth power. So 2 to the fifth power gives us 32. So we have 32x to the fifth power, and anything to the 0 power is 1. So that's, you don't have to write that. Anything times 1 itself. And then we have 2 to the fourth power times negative 3 to the first power. 2 to the fourth power gives us 16. And the x to the fourth power is x to the fourth power. Negative 3 to the first power is negative 3, and then I have a y to the first power. So this multiplies to give us 16 times 3 gives us 18, 48. 48 x to the fourth, y to the first power. We need to write the y. 2 to the third power, 2 times 2 times 2 is 8, x cubed. A negative raised to an even power is positive, so that just means 3 squared. We have 9, y squared. Don't forget the square applies to each one. So 8 times 9 is 72, x cubed, y squared. All right, the square applies to each one, so that's 4x squared. Negative 3 raised to the third power is negative 27. Y to the third power, we multiply them and we'll get an answer. And we do that for all of them. And here we see that it's written just like how we set it up. All right, now the expression, we need to find the row that corresponds to this problem from Pascal's triangle. Again, your cheat way is looking at your second number. Our exponents raised to the fifth power. Let's choose this row that has a 5. So that's 1, 5, 10, 10, 5, 1. Okay, so now we're going to take our setup above and line it up with the numbers we have, so that we have this type of lineup. And you multiply them, and it's set up right here. If I were you, I would clean the first row up, just like we were doing, before I bring in these other numbers. This is our final answer. Now, notice when you have a minus, the minus works in the order so that your first number is always positive, and then negative, and then it continues that pattern. Positive, negative, positive, negative. If your numbers are both positive, like our first example, you see how we have a plus sign, then they're all going to be positive, just like we see here. So in case you don't like keeping track of your negatives, you can make sure that at least it starts positive, goes negative, positive, negative, if you have a negative. All right. Another way to work this out without using Pascal's triangle is the binomial theorem. So this is without Pascal's triangle. Using Pascal's triangle is helpful for relatively low power of binomials, but as we increase the power of the binomial we wish to expand, we use factorials and the binomial theorem. All right, so factorials, we'll talk about them next. For the most part, feel free to use your calculator. Don't feel the need to show your step or to build it by hand. You can, you absolutely can, but I don't want you to take up too much time with that. Use your calculator. All right, so first we need to introduce the concept of factorials. Definition. If n is a positive integer, n, factorial, written as n exclamation point, is the product of all integers from n down to 1. Product meaning multiplication. Definition 2, 0 factorial is 1. Example 2, calculate each of the following factorial expressions below. All right, so this just means if I see a 5 with an exclamation point, it means I want to multiply 5 by every number from 5 counting down till you reach 1. So this is 5 times 4 times 3 times 2 times 1. You get 120. Well, you can go ahead and sit there with your calculator and type in all these multiplications. This one isn't so bad. Find the button in your calculator. Usually it's like an X exclamation point or maybe just an exclamation point. If you're unsure, you can Google search or maybe search on YouTube factorials followed by your brand of calculator or your model of calculator, and you should find the video that helps you work your way through that. All right, example B, 8 factorial. That just means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And our answer is 40,320. In general, every factorial of positive integer n is defined as your number minus 1 minus 2 until you reach 1. As we move toward the binomial theorem, we will calculate some rational expressions involving more than one factorial. For any two non-negative integers n and k, the expression nk reads as n choose k is defined as, all right, so this is also called combinations. And this is, well, if you go on to take statistics or maybe a probability class, it goes the way of choosing an order. For this purpose, we're going to use the formula. We have n factorial divided by n minus k times k factorial. Again, please use your calculator for this. It might change. Usually I see NCR as a button in your calculator. It might be the shift button, so it might be above in different colored writing from your button. But make sure you search it. You can also search your calculator and combinations, and maybe you'll find something that way. All right, I'm going to show you by hand how it works, but please try your calculator and make sure you're getting these answers. It should take, you should take the time to search it. It shouldn't take you too long, maybe like a good 3 minutes of watching a video, and you'll figure out how to work these buttons and save yourself all this trouble. So I'll do B and C. So we have 4, choose 1. 4, choose 1. All right, so we have our n is 4 and our k is 1. So according to our formula above, we see our n is 4, so we have 4 factorial divided by n minus k. So 4 minus 1, exclamation point, times our k, 1 exclamation point. All right, 4 factorial is 4 times 3 times 2 times 1. 4 minus 1 is 3 factorial times 1. So we have 3 times 2 times 1, and then lastly our 1. We multiply them out, and our answer is 4. Also, things will cancel out if you want to think of it that way. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. So we're left with 4 over 1, which is 4. Example C. Your n is 4, and your k is 2. So above we have our k, which is 4 factorial. On the bottom we have 4 minus 2, and then our k. So 4 factorial above in the numerator, it's 4 times 3 times 2 times 1. 4 minus 2 is 2, so we have 2 times 1, and 2 factorial is 2 times 1. And again, you can see how things divide to make 1. Or, yeah, so 2 divided by 2 is 1, 1 divided by 1 is 1. 4 and 2 have a common factor of 2, so we're left with 2 times 3 over 1, so we have 6. Alrighty. Now consider the sequence of numbers above compared to the row from Pascal's triangle linked to the power 4 binomial. They're both the following sequence. So from the problems we did 4 from 0 through 4, and we see that our answers line up to that of Pascal's triangle. Therefore, as powers of a binomial approach much higher numbers, we use factorial expressions to calculate the coefficients. In general, the binomial theorem can be written as follows. So these numbers, those are your Pascal triangle numbers. You can use Pascal's triangle if you like, but I think this is nice to do because what if you make a mistake building Pascal's triangle? I don't know, maybe you didn't line them up correctly. This will keep you from making a mistake of that type, especially if you're using your calculator. All right, example 4. Use binomial theorem to write the first 5 terms of the expanded form of each of the following expressions. All right, I'll only go ahead and do the first one for this one. Yeah. All right, so we want to find the first 5 terms. Notice our exponent is 16. It would take a long time to write down Pascal's triangle all the way to we have a second term of 16. So for this reason, binomial theorem would be ideal. All right, so let's go ahead and set up our numbers. So we want the first 5 terms. So let's go ahead and set it up. I don't know why, for some reason, again, writing it vertically makes more sense to me. So I start with 16, choose 0, 16, choose 1, 16, choose 2, 16, choose 3, and it wants the first 5, so 1, 2, 3, 4, one more. 16, choose 4. All right, let's go ahead and set up our x's and our y's. So our first term is just an x. So whatever that number is, that term, we're going to write it in parentheses. And then we have to write the matching exponent. So it goes up and works its way down. So 16, 15, 14, 13, 12. And secondly, we have that y. So then we're going to write our y in parentheses and match it up. And then we're going to start with 0 and work our way up. So 0, 1, 2, 3, 4. All right, and we're done. Now it's just a matter of using our calculator to find out what, well, a number, when you're choosing a number to 0, it's always 1. But choosing a number to 1, it's always itself. But then after that, it kind of gets tricky. So use your calculator for these numbers. Don't do it by hand. But if you want to, here are your answers. Now from here, all we have to do is clean up our work. So you have it written here horizontally, which I don't know why, it just hurts my eyes and it's hard to keep track of the work. But don't listen to me. If you like this, write it horizontally. And this should be your answer. All right, that's binomial theorem. Again, use your calculator to find these numbers. If you want to do it by hand, that's great. But I highly suggest your calculator. I even think your phone can do it too. Or maybe you can Google 16, choose 3, for example. All right, that's it for this section. And that's the last section that we'll be covering this week. If you have any questions, please make sure to email me. Thank you.